Okay, so let's start. Hello, everyone. At least Zhang is here. So let's start with this tutorial on recent advance on automatic dialogue evaluation metrics. This tutorial is presented by Chen from NUS, by myself, Luis Fernando from Universidad Politécnica de Madrid in Spain. Okay, let's go through the content of the presentation. This is the overview. First, we will go through an introduction. What is a dialogue system? How do we measure progress on dialogue system? Especially, we will focus on human and automatic evaluation systems or models. Then we will have two main components or two different types of evaluation metrics. One is what we call reference-based metrics. We will see those metrics that require training and those metrics that do not require any training at all. We will be spending around 30 minutes for this part of the tutorial. Then we move into reference-free metrics. This is the largest part of the tutorial because it's the current trend and the most important mechanisms that we are developing right now for dialogue evaluation. Again, we have untrained metrics and trained metrics. So we will be explaining different approaches at tone level, at dialogue level, but also untrained and trained metrics. This part will be mainly covered by Chen. This is part of his current research. He will be explaining many different options, current options and state-of-the-art models on this. So we will finalize with the challenges and future directions for this field, for this topic, the things that we need to continue working on that, and we finally have some conclusions. Okay. So, but before starting this, I would like to check with the current participants, how many of you have experience working on dialogue systems or evaluation metrics? Can you raise your hands or open your mic for one moment and tell me if you have experience or previous experience on evaluation metrics or dialogue systems at this? So feel free, please, to open a little bit the microphones and tell us. Yuan or San, do you want to share? Or can you raise your hands there if you have experience on dialogue evaluation metrics? Okay, I guess the answer will be no. So we will try to go from the very basics so you can at least understand the most prominent efforts and ways. So we have tried to create this tutorial with different ideas in mind, having people with a lot of knowledge or having people with just basic background. So don't worry if you don't have really a lot of experience on this. The idea of the tutorial is to teach you all the way through the main metrics and main approaches. Okay, let's go for the introduction. So as you may know, or I can explain this, we have basically three different types of dialogue systems. One, what we call is task-oriented dialogue systems, where the idea is to complete a task. So usually if you want to buy a ticket, if you want to fly to somewhere, so you have in mind exactly what you need to request from the user in order to accomplish this task. So in this case, we call them task-oriented because all the chatbot, all the dialogue system is based on this transactional nature of collecting data from the user because we need those data in order to perform the specific task. Here, success is measured basically in terms of efficiency and brevity because you want the user to get the information as soon as possible or to buy the ticket as soon as possible. And you want to be able to handle all the possible combinations of problems that the user could have. Let's say I want to book a table for 5 people, other ones to have a booking the same table but for 10 people, so on. So you may have a lot of range of variabilities, but at the end, the questions or the things that you need to ask the user are exactly the same, because basically this covers the whole range of possibilities in this specific topic. So if you want also, there is another kind of dialogue system that is called chat oriented. In this case, what we want is to have meaningful conversations. We want to chit chat, we want to have some entertainment. Here, we can be switching from one domain to another domain. We can be talking about movies. We can later move into talking about music or sports. So you can be talking about any different things, but at the end, what you want is to have this engagement with the chatbot. So here, the success is measured in terms of more time for the user interacting with the system, and also probably some ratings at the end of the interaction with the user. Here, usually chatbots needs to be empathetic, friendly, because you want the user to feel comfortable talking to the machine. And finally, we have interactive question answering systems, where basically you want to ask some few questions, then you get the information that you need, and then probably that's all that you need. And here, the success is measured in terms of response correctness. Maybe you just need one single turn to get the information that you need, and then you left, or maybe you need few turns to get all the information, or to ask different questions on the same topic. Okay, so when we measure or when we develop task-oriented dialogue systems, usually we combine rules and statistical components. So in this case, we have seen a transition from very old times when we have many different components to systems that are end-to-end. And here we wanted to give you some few links or papers that relates to the idea of task-oriented dialogue systems, but with neural networks. So I'm not going to enter into all the details of each of them, but in principle, most of the times what you are creating here for task-oriented systems is using rules and some components, unless you move into end-to-end approaches. But again, most probably you will be requiring the system to learn the rules, the steps for the system to get or collect the information. When we evaluate this kind of dialogue systems, as I mentioned before, the thing that we are measuring here is task success and dialogue efficiency. Probably the most well-known framework for evaluation was Paradise. This was proposed in 1997. It's a framework where basically you measure the system based on ratings. So at the end, the user rates the dialogue system at a dialogue level, but you try to learn using some linear regression model how the user how the user was satisfied with this system. So you have basically dialogue scores, you have task success, and you use this information to learn some regression model to be able to get information. Sorry, you have the survey on user satisfaction, and you try to learn the dialogue scores and task success based on this user satisfaction. So there are many features that you can be learning, but at the end, you want to have something that correlates with the survey that you do to the user at the end of the dialogue. So if the user say, I like this system, and the user says, I want to give 5 stars, then you check all these features that you have been collecting along the dialogue to check how you can convert this satisfaction score into different parameters inside. For instance, for dialogue codes, you may be looking into the time that the system was taking for completing the task. You may be looking into the word error rate, even, because if the word error rate of the system or the ASR is really low, that means that the system is going to move faster, and then you will get the information quickly. So in those cases, we check the performance, and we learn this linear regression model. If we move then to the evaluation, usually we measure sentence level semantic accuracy. We also measure a slot error rate. We use F measures because we want to make sure that all the information that is required for providing the task or completing the task are correct, and you are extracting that information correctly from the dialogue or from the different terms. Then also you can have this joint goal accuracy metric that is very famous, very well known and used, because you want to check also the capability of the system to learn all these concepts and get at the end the final result correctly. There are other evaluations based on NLG approaches like correctness, like at the F1 score, or you can have also quality of the surface realization of the dialogue based on metrics like BLEU or Rouge. This will be explained more in detail in the following slides. So when we move into dialogue systems, open domain dialogue systems, then we have basically here systems that are based on retrieval methodologies like dual encoder LSTMs, conv-RT, verb-based, polyencoder. What basically you are trying to do here is to check what is the question from the user, and then you look into your whole list of dialogue or previous dialogues, and you try to find the sentence that is similar to what the user is asking, and then collecting the specific answer for that sentence, for that question. So here what is evaluated, especially because it's a retrieval-based approach, what you are basically looking here is the MR, the mean reciprocal run, meaning that you retrieve information and the first option, the second option, the third option are correct. And if your correct option is lower, then you penalize the system because it's not selecting the first one as the best retrieve item. So metrics from the retrieval approaches are very common here. We are not going to enter too much in detail here because those are basically all approaches, and we want to move more into the more recent approach. Then also for dialogue systems, we have the end-to-end generative approaches, like we have the HRED or VHRED. Those are based on sequence-to-sequence models using RNNs. Then we move into transformers. Let's say we have the GPT, dialogue GPT, the Lambda, or these days, you know, we are moving into more complex systems based on encoding, decoding models like Plato, Mina, Blender, or this very famous chatbot these days, dialogue chat, right? So then for the evaluation, we have ChatGPT, sorry, that's the name of the chatbot that these days are very famous in Twitter. Then we have these evaluation metrics we use to evaluate humans. Humans evaluate the dialogue. They use ratings or Likert ratings at turn or dialogue level. The Likert ratings is, let's say, from 1 to 5. If you give 5 stars, that means that the chatbot is really good. Or if you give 1 star, that means that the chatbot is not competitive enough. Then you can have also pairwise comparison. That means that you can check the performance of one chatbot against another. We will go into more details of this, but basically here the important concept is that humans are there to evaluate the system. Then we have also evaluation based on automatic metrics. Let's consider reference-based metrics like BLEU, Rouge, that we will be explaining later, or reference-free metrics like Perplexity, USR, and others one that we will also explain. And we have this ChatGPT. This ChatGPT, I guess you have been familiar with that because it's very on top of the news in Twitter. Everyone is talking about that one. If you haven't, then go, because you will be surprised by the capabilities of this system. So the question when we see the outputs of this kind of system is how good are these models and how can we measure if these answers are really good or not. And many people are questioning now if this kind of system has made the evaluation basically done or not, because they say those systems are so good that basically the evaluation will be always hard. But I don't think we can just say that. We definitely need to go for new evaluation metrics or more complex evaluation metrics, because at the end, you want to make sure that the system is faithful, that the dialogue is safe, or there is consistency in the long term. You may have a chatbot that is creating very, very good answers, like these ones on the left, but at the end, when you check sometimes they make mistakes, and those mistakes could be very dangerous to do. So we need to continue working on evaluation, because this is critical for the performance and the improvement of this kind of systems. Okay, then let's move into how do we measure progress. We have mentioned that we have different ways to evaluate. Basically, humans are the most reliable or the more important ways to evaluate dialogue systems, because humans provide accurate evaluation, because they are holistically understanding the dialogues. They also evaluate, or humans evaluate, multi-dimensions, different perspectives of the same thing. And at the end, we can also agree from different annotators on this majority opinion. Of course, everyone has a different opinion of something, but at the end, there could be an agreement that a dialogue is good or not based on majority votes. When we also talk about human evaluation, we may have different ways to evaluate, or the human to be there to evaluate. For instance, you can have single model per turn. In this case, the chatbot is providing terms, and every term, the human will check the quality of the answer of this chatbot for that particular term. So you see in the gray color, there are the answers from the humans. So the humans are supposed to be always correct, but we want to check the performance of the chatbot. So we evaluate each of the terms by the chatbot and say if it's good or not. Or we can provide stars. Let's say, we can say at dialogue level, we say, okay, I check the whole dialogue, and at the end, I provide 5 stars, 4 stars to this chatbot. We can have also pairwise per turn evaluation. In this case, we have, let's say, 2 chatbots chatting, and then the human will say chatbot 1 or chatbot 2 is better in turn 1 or turn 2, and this information will go one turn by time. Or we can have pairwise per dialogue. In this case, the human will check the answers from chatbot 1 or chatbot 2 and decide that chatbot 2 is better than chatbot 1. And finally, we can have also chatbots chatting itself. So you can see here, chatbot is providing answer to its own response. Then after that response, the chatbot is asked to provide another response. And then finally, a human will say, okay, I prefer chatbot 1 or prefer chatbot 2. There could be also different evaluation criteria. Let's say turn level. We can see here grammaticality, relevance, informativeness. We can check if the chatbot is emotional or not, if it's engaging or not. So we have different dimensions at turn level. And then we can have also different evaluation criteria on dialogue level. So the dialogue level is more complex because it needs to check the whole dialogue, not only one single turn, but again, you can check for coherence, for consistency, diversity, informativeness, and all this information or all these dimensions are important to evaluate the chatbot. However, human annotations are very, very difficult, right? Because we need consistency, and sometimes when you ask experts, they don't provide the same answers as non-experts, or if you ask crowd workers. It also depends on the age, the mood, the math, the culture, the topic knowledge, the experience that this evaluator has from the past, or the expectations of the evaluator on the particular chatbot. So all this creates variability in the human annotations, and that makes it difficult sometimes to get accurate responses from different people. Besides, it's costly, time-consuming, especially if you increase the number of dimensions that the user needs to evaluate. This will create even more effort for them to spend. Then it's highly conditioned on the evaluation setup. So if you clearly not describe the task for the evaluator, he will be evaluating something that is different to what you expect. So it's very critical to have a clear description of the task. Also selecting the annotators. If you don't check the quality of those annotators, at the end you have a lot of scores, but those scores are not useful. So that's why we need automatic evaluation metrics. But remember, the goal of the evaluation, of this automatic evaluation, is not to replace the humans. We want to supplement it, because this way we create consistent, reproducible, efficient, and cheap process. What are the advantages or the attributes that we want to check for these automatic metrics? We want to check a strong correlation with human judgment. We want also the system or these metrics to be interpretable, multidimensional. They need to be also generalizable across different domains. We need also to be able to have robustness against adversarial attacks. What happens if you change one sentence with another and the system is not able to detect that you change completely the meaning of the dialogue because you move one sentence or you completely change the meaning of that sentence. And at the end, we also want this compatible with human evaluation, so human can be also in the loop at some point. And we have different categorization of metrics. And I want you really to pay attention to this slide, because this will mark the rest of the slides that we will be presenting. The first thing is that we may have what we call reference-based but context-free metrics. What is reference-based context-free metrics? That means that when we introduce to the model, we introduce references, goal reference, the reference that the system should be providing. It could be a single reference, or it could be multiple options for the same, but at the end, you have references. And then you have your hypothesis, and then you need to check how good is the system on this hypothesis or this answer in comparison with the possible good answers that the chatbot should provide. But when we move into context-based metrics, we can have also with or without references. Imagine that we have references. In that case, we have context, reference, and hypothesis. What is context? Context in this case means previous terms, previous dialogues from the same system. So in this case, the system receives as input not only the references, the reference could be optional, but it receives not only the reference, but also the context. And what you need to check is how the hypothesis is related to that context and how the hypothesis is related to the reference. So if you have context, then you can use it. If you don't have, then you may have hypothesis and also a reference like in the previous case, right? And again, we can have untrained or trained metrics. Okay, we are here now. I would like to ask if you have any question that you want to ask at this time. You can open your microphones and ask the question. Otherwise, we will be moving to the next part. Is there any question? No questions? Okay, if this is easy, then let's go to the next part. So here we are going to start with the reference-based metrics. Okay, so for the first part is untrained metrics. Remember, untrained metrics means that we don't need to train a model. We just base basically on surface level information. The first kind of metrics that we can find in the literature are character-based metrics. These metrics work at character or phoneme level. In this case, we are considering only lexical consistency. We are not really checking fluency, syntactic, or semantic integrity, because we are going character by character. So we can have examples of this like a deep distance, Jacquard, Hamming, character, extended distance. So what are the purpose of those metrics? Basically, robustness. If you make mistakes in the transcription, or you make some mistakes on the user answers, so the system is robust against them because it's checking at character level. But really, in dialogue systems, we don't use these kind of metrics. So we are showing them, but we will skip them because they are not really frequent in dialogue systems. Then we have the engram-based metrics. These are based on word level or sequence of words like engrams. And the most common examples are Bleu, Rouge, Meteor, and Cider. Those are the typical metrics that you will find in the literature. And even up today, and we will see some problems with these metrics. There is no any paper basically that they don't provide this kind of metrics. And when we read also in machine translation papers, we also find this kind of metrics. And these metrics comes from the machine translation field, and they come to dialogue systems, but as we will see, they are not really suitable for dialogue systems. But everyone uses them, everyone refers to them because it's easier to calculate. So it's very, very highly used because of simplicity and also because of tradition. Then we have also embedding-based metrics. In this case, we can see people using static or contextual vector embeddings. We probably know about word-to-vec, GLOF as static embeddings, or more contextual ones like using BERT or ELMO. In this case, the embeddings are trained on large corpora, and also they capture distributional similarity between words. That was one of the advantages of using vector embeddings, because they are not just capturing the syntactic properties of the sentence or the words, but they are also capturing semantic information. In this case, we can see greedy matching, embedding average metric. We can see also vector schema, BERT score. We will provide some examples of this, but again, these are not the main topic of the tutorial because they have been for a long time, many people use them, but we are trying to switch to more high-level metrics. Okay, probably you are familiar with BLEU, but if you don't, we will provide some quick explanation of what is BLEU. BLEU is the most popular metric proposed for machine translation, as I said before. It's intended to evaluate adequacy, fidelity, and fluency. So in this case, BLEU is an approximation makes an approximation for precision by using what they call modified n-gram precision. So in this case, what they check is how many n-grams or the fraction of n-grams that are in the candidate text, which are also present in any of the reference texts. So in this case, we are talking about reference-based metrics. So you need to have the references, you need to have the candidates, but then you start checking how many n-grams they share between each other. So the more number of n-grams or the higher order of n-grams, then we say that the system is better. Here, we also need to avoid having repetitive words or having arbitrary long text. Why? Because if, let's say, I can put all words in a vocabulary, and then because all of them are there and I'm not penalizing the length of the sentence, then at some point you will find those n-grams in the reference, also in the hypothesis. So basically you need to take care that you are not only checking unigrams, but you need to check also sequences or longer sequences like n-grams up to some order. And here we combine different orders of n-grams. So in this case, one of the problems with BLEU is that recall is approximated. There is no this way to measure in BLEU the recall. We are just measuring precision. However, in order to consider recall, what they say is, okay, let's consider that the sentences with same length or longer, they will have more options to be correct. So somehow we try to keep we try to keep sentences that are longer without penalty, but sentences that are very short, we penalize them. So this is what is called brevity penalty, meaning that we try to keep the system generating longer sentences. But if you generate longer sentences, then you may make a lot of more errors in precision. So at the end, recall is somehow there because you are penalizing making errors in precision because of longer sentences. But if you make very short sentences, then you are penalized because you are not capturing all the possible words also in the reference. Let's consider this example, and probably this will make it easier for you to understand what we are trying to do here. So let's consider you have the reference. The way to make people trustworthy is to trust them, right? And we have this hypothesis. Then we have to make people trustworthy. You need to trust them. We check that it's not exactly the same. So, the meaning probably could be similar, but they are not the same. And in blue, we are not considering semantic correctness. We are considering syntactic correctness, or syntactically the same sentence. So we will check, let's say, using unigrams, we will check how many unigrams, how many words appears in the references versus in the hypothesis. So in this case, we check that we have 1, 2, 3, 4, 5, 6, 7 of these unigrams in the hypothesis are also in the reference. So for unigram, we will say the probability is 7/9. And why 9? Because the length of the sentence in the hypothesis is 9. Then you move to bigrams. In this case, you make also count how many bigrams are in the reference that are in the hypothesis. So we can see here, we have 5 bigrams that are also in the hypothesis. So now the probability is 5/8. And you will do the same thing for trigrams and fourgrams. So at the end, you have these results here, 3, 7 or 1, 6. Okay, so you can see that for fourgrams, the number of relationships or the number of matchings is very low, 1, 6, while here the probability is very high. So at the end, you don't consider only unigrams or bigrams. You need to integrate all of them and also consider the brevity penalty. So here we consider what is the size of the reference, the size of the hypothesis, then you calculate the penalty. And finally, you get the blue for M4 like 0.34. What is this? Is this evaluation here? You are introducing the brevity penalty and also the summation of the different probabilities. So at the end, this 0.3 means that the system is kind of okay, but the higher, the better. So what are the problems? Require multiple references for better handling syntactic and semantic differences. We are just considering precision, so we go until order 4 usually. We could go to order 5 or 6, but or 7 or whatever we want, but in general, the longer the number, the higher the order, the more difficult to get good results. So at the end, you don't want to penalize too much the systems. Recall is difficult to calculate. The average length is also modifying the result, and you don't know exactly if that length is good or not because you are not really considering the semantics of the system, of the sentence. Then they invented, or they moved into Rouge. Rouge is basically the opposite to Bleu. They are focusing on recall rather than in precision. So this Rouge is mainly used for summary evaluation, not for dialogue systems. But again, it's very common to find this metric in dialogue systems. So it is intended to measure coherence, conciseness, grammaticality, readability, and also content. We have different flavors of Rouge, but we will focus on Rouge N and Rouge L because those are the most common ones. So for Rouge N, basically you count the number of n-grams across all the reference, and we found how many of them are present in the candidate. This is very similar to what is done in Bleu. It's very common. And then we have also the possibility of considering sequences. In this case, what we call longest common sequence, LCS. And we have other flavors like weighted LCS or skip bigram concurrences. But again, the most common one is longest common sequence. That means you try to find those sentences or those n-grams or sequence of n-grams that are longer in the hypothesis that also occur in the reference. I think we can check again an example, and this will make it easier to understand. So we have again the sentence, to make people trustworthy is this part of the sentence is also in the reference, to make people trustworthy. And then you have to trust them. To trust them is this last part, right? So you can have RLCS, that is 7/10, and you have also precision LSCS is 7/9, and then you combine all of them. And you are combining this because you are taking into account how many of them occurs in the reference, how many occurs in the hypothesis, and finally, you give weight to the recall and precision, and you get something like this, 0.73. So here, the higher, the better, because that means that the system is basically having sequences of sentences that are exactly the same in the references and in the hypothesis. And then we move into embedding metrics. We mentioned that there is greedy matching or average embedding. So what do we do here? Basically, we have word embeddings for each word in the reference or each word in the hypothesis. And then we do greedy matching. That means that you will go word by word in the reference and word by word in the hypothesis, and you will check which ones are closer to each other. And then you select the one with the max value for the cosine similarity. So if this word, I don't care about the order, but if this word is close to that word here in the hypothesis, then and the cosine similarity is higher, I will take that value. Then I move into the next word in the hypothesis. Then I will check all the words in the reference. And again, I go to the end of the sentence. And when I finish with the hypothesis, I will move into the reference. And I need to do the same thing. Why? Because there is the direction dependent. So you need to consider both sides. So that's why here in the formula you have you divide it by 2, because you need to check from reference to hypothesis and from hypothesis to reference. Or you can have something very cheap, very fast to do, that is average embedding. In this case, you compute a sentence embedding, a sentence level embedding. Then by averaging the word embeddings or creating a sentence level embedding, and at the end you check the cosine similarity between the hypothesis and the reference. And that similarity is basically your distance between hypothesis and reference. What are the advantages here? That is a cheap metric, but at the same time, it's a metric that is considering not only syntactic similarity, but also semantic similarity, because these sentence level embeddings or word level embeddings, they capture not only semantics, but also syntactic information. Or we can have BERT score. This is probably one of the most famous at this time embedding metrics. Is based on calculating the cosine similarity for each hypothesis token J, which is token I in the reference sentence, but in this case using contextualized embeddings created by BERT. You know, BERT is transformer based, is having contextual information better than only static vector embeddings. So at the end of the day, you do a similar approach as the greedy matching, but in this case using vector embeddings based from BERT, and that will provide similar results, but because of the contextualization, probably your results are better than if you rely on the greedy matching or average embedding. And finally, we have the adequacy and fluency metric. This was initially proposed by Bunch and by myself in 2014 for machine translation, but later we modified this for open domain dialog system. And finally, Chen also, he worked on this metric. He improved it through the integration of transformers, replacing the previous metric by using contextual embeddings using BERT as well. So what we do here, what is the main core of this AM-FM metric? We are evaluating basically 2 dimensions. One is adequacy, that means coherence with respect to the context of the reference, and fluency. So basically we are measuring syntactic and semantic similarity between the hypothesis and the response. So the advantage of this metric is that it's very simplistic. We are just evaluating 2 dimensions, adequacy and fluency, so it's very easy for people to understand. And at the same time, it could be context dependent or no context dependent metric. We can have references or we can have only context, so it's very flexible in this sense. And we also have the possibility of changing length of the sentences. So at the end, I don't care too much about which sentence is longer, which sentence is shorter, because we use relative scores. And actually, this metric also has been adapted to handle multilingual data by changing the encoder into a multilingual encoder. And we have been using this metric for machine translation metrics also in WIT. It's a challenge for machine translation that is very famous because it's on Asian languages. And every year that is run, we provide AM, FM, adapting to the new languages, and it's very easy to adapt to new languages. So here we can see the formula for AM. Basically, what we are doing is cosine similarity between references and the hypothesis. And for FM, what we are checking is perplexity. But because we want to have a relative score, so we select which one is providing the minimum perplexity, and we divide it by the maximum perplexity between the perplexity of the hypothesis and reference, or also divided here for the one with the higher perplexity. So at the end of the day, what we have is, if the sentences are similar, they should have similar perplexity. If the sentences are correct grammarly talking about, then they should have similar perplexity as well. And if the sentences are close in the semantic space, then the AM should be able to provide this result easily. Then we move into train metrics. We can have here context-free or context-based metrics that contain learnable components trained for automatic evaluation. In this case, what basically people are doing is to combine different heuristics features that we extract from the dialogue, and then we train a system or a model to be able to predict the goodness of this metric. So what we use here, for instance, we can be extracting as features the engram precision, we can be extracting the recall, the BLEU, meteor scores, but at the end, we want to use, let's say, an SVM model, like in the case of Blend, or we may be using some linear regression model to put all this information, all these features, and then try to create or to predict what will be the output from humans. So we have a regression model, we train the model, we train the weights for each component, but at the end it's very simplistic because we are considering here the necessity of having humans to provide the scores. We have also, depending on the number of features, we may have a more difficult metric, but at the end, it's also for you humans very easy to understand, because you will see based on the weights given to each feature, which one contributes the most to the selection of the final rating. So it's very easy to understand. There are different flavors. Here we are just presenting some few of them. And then we have BLEU RT. BLEU RT basically is moving into end-to-end. This was one of the first systems moving into transformers models, and they also take advantage of these transformers for moving into contextualized word embeddings. So you need also to train this based on evaluation with humans. But the advantage of BLEU, or the main point with BLEU RT, is that they pre-train this bird based on millions of synthetic examples, because they wanted to have a system that is generalized, that is able to generalize and also able to handle multiple subtasks. So basically what they did is, okay, I have human evaluations, so I will be fine-tuning my model on those human evaluations. But before doing that, I will be training the system with different tasks or automatic tasks to predict when this sentence is synthetic or is real, and the system learn to be robust for different variations of the sentence. And okay, this is the last part of this section. If you have any question, this is the time, or otherwise we will be moving into the next part. Is there any questions from the audience? Everything is clear? So far, so good? Don't be shy. If you have questions or something is not clear, just this is the time. Okay, so no questions. I think it's time to move into reference-free metrics. So now is your time, Chen.
Okay, so hi everyone. Luis, can you hear me?
Yes, I can hear you. And I think you should be able to have also control over the screen. If not, yeah, you should be able. Okay.
Okay. Okay, so yeah, thanks Luis for the detailed introduction of the dialog system in general and the reference-based matrix. So now let's dive into the reference-free matrix, which is try to address some of the problems that are encountered by the reference-based matrix. So by reference-free, we means that the input to the matrix is just the context as well as the hypothesis. So we don't do quality estimation based on the reference, human written references. The first problem with the previous mentioned reference-based matrix is that they correlate poorly with the human evaluation. So as we can see here, for on the right figure, when the human score of group 1 and the human score of group 2 actually have a perfect linear relationship. So there's one straight line in the figure, but as we can see, the blue score and the embedding average, their correlation with humans are actually very poor. So the dots are all completely random. So that's one problem with the reference-based matrix. So one cause of that is that because dialog systems for dialog generation tasks is like open-ended generation. So for one dialog context, there may be multiple semantically viable responses. So we need to, like, for reference-based matrix to work well, it needs, like, we need to write many semantic varying references, but that is very costly to obtain. And a second problem with the previous mentioned metrics are that they generally compute a similarity score, for example, between the reference and the hypothesis. This single score, it's kind of hard to interpret. It only like captures the partially of the quality of the response, for example, the adequacy, or is kind of or whether the response is fluent. But there are many different dimensions with respect to the quality of the dialogue. So here we think that there is no one-size-fits-all solution to open domain dialogue evaluation. So we need to design different metrics to tackle one quality of the dialogue. Therefore, it is kind of necessary to rely on the reference-free metrics, or we call them context-dependent metrics. So actually, there are two. We can divide the reference-free matrix into two final groups. One is the untrained, the other is trained. So for untrained, it means that there is no model involved in. I mean, we do not train a model to score the response. We just rely on some heuristic method to compute a score. So one very common measure, reference-free measure, is the perplexity. So for perplexity, is basically used very popularly for evaluating the language model or the text generation task. It measures how well a probability model or the distribution predicts a sample. Here it may be a sequence of words. So in the case of dialogue generation, the input to the language model is basically the dialogue context, and we use perplexity to measure the likelihood of the generated response. So the lower the perplexity, we think the higher the conditional probability of the generated response. So it's commonly used in the literature to tune the model during the development phase. And another untrained metric is the semantic coherence. So it relies on the sentence embedding of the context and the hypothesis. So we try to compute a similarity between the hypothesis and the context. So it's a kind of coarse way of evaluating the local topical coherence. So it's like it works similarly for the reference based matrix as a embedding based reference based matrix. It's just we just replace the reference here with the embedding of the previous utterance of the current utterance. So the performance of this matrix actually largely rely on the encoder, the text encoder we used. So the better the semantic representation of the context and response, actually the better the performance will be. Then another way to realize this matrix instead of using cosine similarity is to rely on a pre-trained NLI model to predict the entailment between the context and the response. So basically, that's the two metrics for the that are untrained reference matrix. Now we dive into the details of the end-to-end training-based reference matrix. This is kind of the current trend of the in open domain dialogue evaluation. So we rely on a model to score the dialogue or the dialogue response. So there are three actually important aspects that are relevant to the end-to-end training-based matrix. It's basically the first one is self-supervision. Basically means that we don't rely on any human quality annotations to train the model. Instead, we just train a matrix on unlabeled, large-scale unlabeled human dialogue data. So in order for the self-supervision to work, we need to rely on some negative sampling strategies to construct negative samples, or we need to construct different negative samples so as to train the matrix to distinguish the positive sample from the negative ones. So here we can see an example here. We have the dialogue context, then we have the original ground truth response that is derived from the human-human conversation. Then we rely on the random utterance sampling strategies to obtain one response from a different dialogue. So we try to train a matrix that is able to tell the ground truth from the random response. So it's just an example of the negative sampling. Of course, there are many different sampling strategies to improve the matrix performance. And third important aspect is the reliance on pre-trained language models. So as of now, the pre-trained language models are already like very common in the NLP applications. So for our end-to-end matrix, we just incorporate the model as part of the end-to-end pipeline to provide semantic representation of the input sequences. So it's kind of kind of common practice nowadays. So before diving into details of all different representative training-based metrics, we may first want to know the commonly used human dialogue corpus that we adopt to train the matrix. So basically, there are like four common domains that we use to train the matrix. One is the daily chit chat, which talk about the daily style like conversation, such as about our hobby and life, everything. And the second domain is the knowledge grounded conversations. So basically means that the two people the two parties in the conversation will discuss topics that are grounded on the external documents, such as the Wikipedia page or some articles in the newspaper. And the third domain is the personal guided conversation. This means that there are two, like each speaker in the conversation, there is they will have a personal profile associated with the speaker. The personal profile means that it's a set of utterances that describe the hobbies, the personality of the speaker. So they try to engage in a conversation and introduce introduce themselves and discover some mutual interest. Then the last domain is the emotional dialogues, which means that the dialogue will discuss some emotional context. Then one speaker will convey their emotions, what they have been experienced, and then other speaker will act as an empathetic listener. So these are the four domains of the commonly used dialog corpora. And here is just a list of statistics of the different representatives of dialog corpora for each domain. So of course, for open domain dialog research, there are like much more dialog corpora than what we have been through, what I have go through just now. So so actually in GSTOR 2022, so the 7th Frederick Jennings Memorial Summer Workshop hosted by Johns Hopkins University, our team actually created a list of 18 dialog data sets, open domain dialog data sets. So we try to unify the format for easy processing, and we also provide additional annotations such as sentiment, and we translate the original English into other languages such as Spanish to facilitate multilingual research. So we also open source all the data sets in the GitHub link here. So as to facilitate maybe future research on open domain dialog generation or evaluation, you may feel free to access this link here to get a copy of all the data sets. So now let's dive into the details of the training-based metrics. So the training-based metrics can also be categorized into turn level metrics and then dialog level metrics. So by turn level metrics, we mean that the dialog will only evaluate the quality of a single response. So by dialog level metrics, we mean that we want to evaluate the quality of the dialog, the multi-turn dialog. So it's like a kind of a local evaluation method, local evaluation metrics versus a global evaluation metrics. So the first representative example of the turn level metrics is this Ruber reference and unreferenced metric blended evaluation routine published in III 2018. So the Ruber is basically is introduced to improve the reference component mentioned, the reference-based metric mentioned previously. They try to improve by introducing a unreferenced component. So the reference component is just rely on the computation of cosine similarity of sentence embeddings between the ground truth response and the generator response. It just measures the adequacy of the generator response. So it's kind of similar to what Luis mentioned previously. And the additional component is just the unreferenced part, whereby the authors trained a neural network to model the relevance of the generated response and the query response. So by query response, we mean that it's a query utterance which is the previous utterance within the current response. It means that, for example, I ask, how are you? Then the system may generate, I'm fine, thank you. So the query is how are you? Then the generator response is, I'm fine, thank you. So this unreferenced scorer is basically a neural network of a simple two-layer feed-forward network with a sigmoid activation function after the output layer. So the model is basically trained in with the margin ranking loss. It is trained to give a higher scores to the ground truth replies than a random response from other different dialogues, because previously we mentioned that the model will rely on some random sampling strategies. So we just to predict higher score for the ground truth and give a lower score to the random dialogue. So in this way, we can train a model to train a matrix in this manner. And after that, the score of both reference component and the reference-free component are combined to derive the single Ruber score of the response. So the author kind of observed that there is an increase in correlation with human evaluation by introducing the reference-free component. So that's that early work of the reference-free metric. So next is the representative example is the BERT ruber. So introduced in NARCO workshop 2019. So in 2019 actually is a kind of game-changing year for NLP. So the pre-trained language models based on bidirectional transformer encoders such as BERT and Robota actually completely changed the NLP field. So similarly for the open domain dialogue evaluation. So the author basically tried to improve the original, the previous mentioned ruber with contextualized representation provided by the BERT encoder. So for the reference, for example, on the right, for the reference component, instead of using word-to-vec embedding, they just use a BERT encoder to provide a sentence level contextualized representation for both query and the response. Then they compute the cosine similarity of the embedding vectors of the response and the query. And for the unreferenced component, they modify the embedding layer. Originally, they use word-to-vec embedding. Then the authors just replace it with the BERT embedding. Then after that, use the max pooling operation to derive a sentence level vector representation. Then instead of using the margin ranking loss introduced in the original ruber, they just replace it with an MLP classifier to perform the task. So the takeaway message of this representative example is that the contextualized representation provided by pre-trained language models such as BERT or Robota can actually indeed improve the metric correlation with human evaluation. Okay, so the third representative example is the MAUDI, which is so because the reference frame modeling of the ruber and the BERT, they are kind of problematic because firstly they are designed for static evaluation. This means that they only evaluate the local contextual relevance of the context and the response. So if you recall in the previous slides on human evaluation, in the per turn evaluation setup, we would like to evaluate dialogues turn by turn in an interactive manner. But the ruber and the BERT ruber are not designed to handle such situations. So in this ACL 2020 paper, they propose MAUDI to target evaluation in such a setup. So basically, compared to ruber and the BERT ruber, which just simply use a random sampling strategy, the MAUDI actually also additionally propose use a variety of different sampling strategies that were introduced in the following slides. So firstly, let's look at the entire architecture of the MAUDI framework. So the input, as we can see on the right figure here, the input to the MAUDI framework is a sequence of utterances, and the output is a single scalar, indicating the quality of the current response. Here, that's a lot of money with respect to the entire context, which consists of the first 5 utterances. And we use the BERT encoder to map each utterances into an embedding representation. Then a max pooling function is used to convert all the sentence embedding vectors of different context utterances into a single context embedding vector. And then after that, we concatenate the context embedding vector and the response embedding vector, and use a feed-forward network is adopted after the then the concatenation vector concatenation is input into a feed-forward network, and the entire matrix is trained end-to-end with this lowest contrastive estimation loss. So in order to train the model, we need the original response like this, and also negative response that are obtained with negative sampling strategies that I will introduce in the next slide. So in this paper, the author proposed 2 categories of negative sampling strategies. One is the syntactic perturbation and the semantic perturbation. So for syntactic perturbation, so it's kind of so we do text level manipulations of the response of just the current response. So it's within sentence perturbation. So such as the word order, like we shuffle the ordering of the word of the response, or we do that word drop, such as we randomly drop X% of the word in the response, such as 15% to 20%. Then we also like do some word repeat operation, like we randomly repeat a span of words in the response. So in this way, we create a set of different negative samples with respect to the original human written response. And the second category is the semantic perturbation. So means that we change the meaning or change the meaning of the response, or we so for the one is the random utterance from another dialogue. So means that we pick a utterance that is completely irrelevant to the current context. Like if I ask how are you, then you reply me by like give a reply like I just like I ask you how are you, then you answer something like so like I'm studying, something like that. So it's topically irrelevant. So the second perturbation is utterance produced by a sequence model condition on the another dialogue context. So means that we sample, instead of randomly sample utterance, we just sample a random context from other dialogue, then use a sequence model to generate a response. So the response should be relevant to the other context instead of the current dialogue context. And the third one is similarly. So, but instead of using sequence model, we just use back translated model. We translate so we translate the utterance. So we first randomly sample utterance, then we translate them into English, from English to like Spanish or German, then we back translate them back to English. So it's like more introduce kind of both semantic and syntactic perturbations. So after that, so we try to assess the performance of the model. So to compare, actually to see whether it performs well, we can actually check the difference between the original response, the original response score given by MODI and the perturbed response score. So for the positive perturbations, like the semantic positive, so the difference should be as small as possible. And for the semantic negative perturbations, or syntactic negative perturbations, the score difference should be as large as possible. So this is to compare with the score given to the original response. So for example, for the back translated response or sequence generation, the score, the difference should not be very large. For example, for the back translation, so the MODI here just the score difference is just 0.07, but for the syntactic negative, such as word repeat, word order, the score difference with respect to the original response is kind of large, 0.8. So this showcases that it is able to tell the difference between the negative sample from positive samples. So then let's look at the fourth example, which is the USR. So as we can, the previous three matrices, previous two matrices, MODI and Ruber, they only focus on the contextual relevance of the response, which is only partially a partial quality. So we want to look into like multi-dimensionality of the response quality. So because the dialogue evaluation is actually multifaceted in nature. So this USR paper published in ACO 2020, they actually propose a set of different desirable properties of dialogue that we ought to evaluate at the turn level. So the first one is understandable. So it's like it evaluate whether the response is understandable in the context of the dialogue history. So basically the dialogue context. The naturalness of the response, so means that whether is more pertaining to the grammar of the response, which is because we know some sequence model tend to generate like not well formed text. So we want to evaluate whether the text generated are well formed in terms of English grammar. So the third one is maintains context. So that's a response serves as a valid continuation of the conversation history. And the fourth one is user's knowledge. So this means that whether the generated response is grounded under external knowledge, whether it's truthfully deliver the information that is covered in the external knowledge base. For example, just now we mentioned the data set, the topical chat. So that one can be used to evaluate, to train models that specifically evaluate such dimension. And the last one, this fine-grained is interesting us. We will try to see whether the response is engaging, whether it is dull or not. And then finally, the overall quality, which is the overall impression of the utterance. And in the paper, the author first proposed construct a high quality data set that's called the USR data set, because in order to benchmark the metrics, we need some kind of human evaluation data sets to assess the validity of the metrics. We compute correlation between the metric score and the human score. So we need a data set. At that time, there are not many high quality human evaluation data sets. So that's one contribution of the paper. So the author basically sample 120 dialogue contexts from personal chat and the topical chat introduced earlier. So each we select 60 dialogue contexts from each data set. So for each context, then they adopt a different set of generative model to generate 6 different responses of varying quality. Some responses are good, some responses are not good. So then there are 6 dialogue researchers. They will annotate each context response pairs along the 6 fine-grained quality introduced previously, like understandable. Then they will score whether the response is understandable or not. So for the overall quality, then on a scale of 1 to 5, they will try to score their first impression of the response. And here on the right is basically a kind of example from personal chat. But if they want to sample the sample context, they just sample, for example, the first 3 utterances maybe. Then they use a dialogue model to generate a response following these three contexts, three utterances. And for the dialogue quality, we usually use the interlocutor agreement to tell whether the quality of the data sets are good or not. It observes that for each dimension, like here, there is a moderate to high interlocutor agreement. So the quality of USR data set is kind of good. So after the first contribution of introducing the USR data set, they try to propose the USR metric. So basically, USR metric consists of 2 parts. One is the mask language modeling, the MLM metric, which is used to evaluate the understandability and the naturalness of the response. What they do is basically they fine-tune a robota-based language model on the personal chat or topical chat data set. Then after that, they try to compute the log probability of each mask word. For example, here, given the context, how are you? Then the original, for example, the general response is I am okay. So they mask 1 word at each time. Then use the fine-tuned robota to give a score. For example, we first mask I, then we try to see what is log probability of the model to predict I, and so on and so forth. Then after that, we add them up, and then we negative the sum. So means that because usually the log probability score correlate in a negative way with the human score. So that's why we negative here. And the second submatrix of this USR matrix is the dialogue retrieval matrix. Basically, it's adopted to evaluate the other 3 fine-grained quality: the maintaining context, interestedness, and the using knowledge. So it actually, the metric relies on the contextual information to distinguish the original response from the random ones. So actually it's kind of similar to what Ruber and the other MOD are doing, but they just adapt this task to evaluate the different qualities by manipulating the context information. So the first setting is like context consists of both the dialogue history and the fact, and they intend to use this information to tell whether to train the matrix whether the response is maintaining the context, as well as whether the response is interesting or not. The second setting is they just introduce the fact into a context without the dialogue history. So they use this kind of setting to train models that to evaluate the using knowledge dimension. So after the introduction of each submatrix, so we need to in a way to combine them together so as to, for example, if we want to evaluate the overall quality, so we need some mechanism to combine the submatrix score. So here basically the matrix here basically tells what the human thinks the importance the human gave to each fine-grained matrix with respect to the overall impression. So it's like for this A1 annotator, he thinks that there is a 0.43 importance in terms of interestingness with respect to the overall. So the contribution of the interestingness dimension should be greatest, but there are other human that thinks that like this A4 annotator, he thinks that the naturalness of the response should be more important. And so we can see that the human actually have different perceptions of what contribute the most to the overall quality of the dialogue. So how do we combine the metrics given that they are like different perceptions? So in general, we just what the authors did is they train a regression model, with the human annotated data. So that they try to like for each dimension, they based on the training method, the data-driven method, they just obtain one weight and use the weight to combine the matrix. Okay, so after introducing the matrix details, we shall look at the performance of the matrix. So basically, the performance is evaluated by the Pearson or Spearman correlation of the matrix score and the corresponding human evaluation score along the different fine-grained dimensions. So we can see here the US bar or its submatrix like kind of outperform the best reference-based matrix across all the dimensions, like the BERT score, which is famous reference-based matrix. And also we can see that the both submatrix like the USR MLM and the USR DR actually like perform as expected, because USR ML are designed for naturalness and understandable. So we can see in the US, so we can see that the USR ML perform well on the corresponding dimension, and the USR DR performs well on the maintaining context and interestingness and use of knowledge. However, we can observe that after combining them, for example, the USR, if we combine the USR DR and the USR MLM, the performance for some dimension drop, and it is actually far from very perfect correlation, because perfect correlation is 1. So they are like kind of not very high here. So there are still significant room for improvement. So let's dive into the next representative example, which is a D-score. So one major issue with USR is that they treat the evaluation of individual dimensions as independent. So this means that there's no correlation at all between different dimensions. But however, in previous studies, we found that human judges actually do not evaluate different aspects in a completely independent manner. For example, in the figure here, the adequacy and the fluency dimensions, basically the human score of adequacy and the human score of fluency, actually they correlate in a very significant manner. So these dimensions are not actually completely independent. So we need to like a way to capture such dependence among different dimensions. So that's why that's motivation of this D-score paper. They basically adopt the multitask learning to learn a holistic matrix that can evaluate the different dimensions such as naturalness, response appropriateness, coherence, and the consistency. So since this score is similar to the other matrix, it's kind of based on self-supervised learning. So we don't use human annotation to train this model. So we need to design different pretext tasks to handle each of the dialogue tasks. Each dialogue aspect. So the first pretext task is to discriminate the original response against the random utterance, which is similar to the previous other matrix are doing. So these kind of pretext tasks aim to capture the response relevance or whether the response is appropriate with respect to the context. And the second pretext task is shuffling order of the utterance. So for example, we have the preceding utterances as the succeeding utterances and the current utterance. We just swap the order of the current response with one utterance in the preceding context or one utterance in the succeeding context. So normally this ordering, shuffling is try to capture the coherence of the responses. So the third one is we try to rely on the third pretext task. We try to rely on the natural language inference task. So basically, we want to show that whether the current response is entailing the prevailing context or it's contradicting the context. And the last task is the language modeling task, which is a standard. We try to evaluate the naturalness of the response. So it's a standard language modeling objective. Then after that, with these 4 pretext tasks, we try to rely on multitask learning to simultaneously train a model that learn all these pretext tasks. Then so the input to the model is just a sequence of utterances, and we use the robotic encoder to encode both the context to encode all the utterances. So for example, this preceding utterance context and the current response through this robotic encoder. So it's like one sequence of embedding vector. And here we concatenate the current response and the succeeding context. This is another sequence of embedding vector. Then through an additional bio-STM layer is to further capture the sequential interactions of all the words. Then after that, we use alignment layer to transform the vectors into a single score corresponding to each dimension. So we see that. So here we look at the performance of the D-score. So here is like a Spearman level, system level Spearman correlation. So we can see that actually compared to USR, here should be USR. Here is the matrix fusion. So this score actually achieves the highest correlation across almost all the dimensions. And in terms of average, it's like the USR can achieve like is 0.279, but the D score is like obtains almost 0.563 correlation score. So this means that this showcases the advantages of multitask learning. So let's dive into the next matrix. So this matrix is called the MDD-Val. So basically actually observe this matrix is published in IIII 2022. So we observe that all the existing training-based metrics, they act kind of like a generalized skill to evaluate dialogues across multiple domains. This means that some metrics perform well on a particular domain, but the other metrics may perform well on a different domain. As we can see here, the DEB and the grade metrics, which are trained on the daily dialogue domain, they generally perform well on daily dialogue benchmarks. By the USR, which are trained on the topical chat domain, they just perform well only on the topical chat domains, topical chat benchmarks. So we want to design a matrix actually that work well across different data sets or different domains. So how do we do that? So basically so there are two like possible solutions. So one is like we can recruit the humans to write like multiple relevant and hard negative responses given a dialogue context. And this dialogue context can come from different domains like personal chat or daily dialogue. But this type of method to collect a large scale multi-domain training data is very expensive and kind of difficult to scale. And there are also other people that rely on data augmentation techniques to mimic the human written way of collecting data. But such way is the quality, there is no quality control. There is a potential to introduce like low quality data, such as the false negatives. For example, some generated response may be correct given the context, but if we use augmentation, it will treat it as a negative response. So it's kind of harmful to the model training. So how can we design, how can we like combine the advantages of both human method, which is high quality, and the data augmentation techniques, which can enable us to collect a large scale data? We rely on this semi-supervised learning method. It's called self-training. It's basically we apply a teacher model, then trained with high quality labeled human data. Then we use the teacher model to create synthetic labels for the unlabeled example that are generated with the data or the data augmentation techniques. Then after that, we combine the pseudo label data and as well as the human label data to train a student model to perform the task. So the step one of this pipeline is first to train a strong teacher classifier, which means that we fine-tune a Robota encoder on a daily dialogue fast dataset. This dataset is a high quality human generated dataset. So it contains like a dialogue context and the human return like relevant response adversarial, and this random response is like randomly sampled from another conversation. So the quality of the data set is good, so we can use it to train this teacher model. So basically the accuracy of this teacher model is able to discriminate, is able to achieve like 80% of accuracy to distinguish all these different type of responses. So the step two is to perform data augmentation to obtain a large scale multi-domain data. So here is the list of strategies. So firstly, in order to obtain the perform data augmentation, we need the source data. So for source data, we sample dialogue context and response from this human dialogue from the previous mentioned 4 different data sets like daily dialogue, person chat, and perceptual dialogue, and the topical chat. Then after that, we can like do back translation of the dialogue response so as to obtain the positive samples. And we also can do like mask and fill strategy. It means that we randomly mask some words in the response, and then we use the GPT model to generate a mask language model to predict the words, like to auto denoise the response. So then use this kind of strategy as to generate the adversarial response. Then thirdly is the random sampling, which is similar to what we mentioned before. And of course, we can also rely on like large-scale pre-trained chatbots such as Dialog GPT and the BlendBot. They are very nowadays. They can generate very human-like response conditioning on the context. They in this way can also generate some relevant and adversarial responses. Then of course, following MAUDI, we have the syntactic perturbations to generate the negative responses. So step 3 is actually the quality check step. Sorry, it's a pseudo labeling step. So we use the teacher model to assign soft labels to the augmented unlabeled data obtained in step 2. Then the soft label is a probability distribution of the 3 classes like random, adversarial, and relevant. Then we adopt a quality check step. So like we keep the data that teacher is most confident about. For example, it assigns the probability. It thinks that the response is relevant 70% of the time. So we keep the data. So we filter out those low confident samples. So in this way, I obtain like a large scale pseudo labeled data set. Then after that, in step 4, we combine this pseudo labeled data set and the original daily dialog process, which is the human labeled data set, to train a student model, which is the same architecture as a teacher model, but initialized with only the robota, the initial weighting initialization. So we train the model with 3 different losses. One is the standard cross entropy loss to tell do the classification task. The mask language modeling loss, which is to adapt to enable the student model to adapt to the the pseudo label data set. Then the Q divergence loss, which is which is a common technique for self-training to regularize the training process. So we introduce some noise to the response, and also as well as the original response. We try to force the model to make the same prediction to the lowest version and the original version. So then we minimize the Q divergence. So we train this model in an end-to-end manner. So that's basically the all the procedure of MDD volumetric. So the performance, in terms of performance, we can see here, the MDDS is the final student model, and the MDDT is the teacher model, which is trained on human label data. And also we compare with DB, which is trained on the daily dialog data, and the USL and the USR here, which we introduced previously, and D-score, which we also introduced the D-score. So we can see here, in terms of the performance across different benchmarks from different domains, the student model performs well. The MDD student model performs well across different domains than both USR and the D-score, as well as the teacher model here is 0.37, and here we obtain 0.47. So basically, the takeaway message is that in order to train this multi-domain generalized model, we need to collect high quality data. So we can always rely on this semi-supervised method to collect large scale data set for training our models. So now basically that's the end of the turn level matrix. Does anyone have any questions? So if not, then you can always post your questions or directly email me if you have any questions regarding all these metrics. So let's move into the next section, which is the dialog level metrics. So the difference between dialog level metrics and the turn level metrics that we look at is kind of global versus local thing. So we look at in global level, the multi-turn, the quality of the dialogue, instead of a single turn, like only the quality of the single response. So that's a difference. So the first example of this category is the FED. Actually, FED is tailored to both turn level and the dialogue level evaluation, but it is kind of the first to introduce a reference-free matrix specifically for the dialogue level. So it's published in SIGDAL 2020, and so basically the motivation of doing dialogue evaluation is that some of the erroneous behaviors can only be captured after observing the entire dialogue. For example, consistency. Only after we interact with the chatbot for several turns, then we can notice that whether the information the chatbot conveyed now is whether it contradicts what it says before. So sometimes if the chatbot may tell you I'm happy, then after continuous interact with it for several turns, you ask him how are you feeling now, it says I'm sad. So it's kind of contradictory. So we want to capture such kind of erroneous behavior. So of course, for both turn level and dialogue level, they have a different set of quality dimensions, means that both have a fine-grained dimension instead of only in the overall overall quality. So we look at different dimensions. And most existing metrics and evaluation data sets are about turn level evaluation. So dialogue level evaluation is only like gain attention in recent 2 years, starting 2021. And so this FED targets the multi-dimensional evaluation at both turn level and dialogue level, and introduce a data set and also a FED matrix. So I will go into the FED data sets. So first, this same group of researchers from CMU, they annotate this they collect dialogues like interaction between human and the state-of-the-art dialogue from Google or human conversation. They try to annotate the interaction both at the turn level and dialogue level. So at turn level, there are like 9 different dimensions they annotated. Here is the score range. 1 indicates, for example, the response is not interesting. 3 indicates it's very interesting. So that's the annotation at the turn level. So our focus is at the dialogue level. So the dialogue level, they annotate along 11 different fine-grained dimensions. So basically, 1 is the coherence. So globally, whether the system is coherent and maintain a good conversational flow. So 1 means not coherent, 3 means very coherent. So they are like 11 fine-grained dimensions. And this FED data sets, basically we mentioned just now. So it's annotated. There are 125 dialogues that come from 41 come from the human Mina, which is a Google chatbot interaction, human me to school, and the human conversations. So there are 125 dialogues that are annotated. So for each dialogue, 3 system responses were hand selected to be annotated at the turn level. So there will be 375 annotated response. And also each dialogue, each data instance is annotated by 5 crowdsourced workers. And we can observe that actually the inter-annotator agreement are quite high for all the dimensions. So most of them are above 0.7. This means that the quality of this data set is very good because the humans are all agreeing with each other. So when we do develop metrics, we want to optimize our correlation with human correlation as high as possible. So this column here kind of serve as the upper bound of the metric performance. So after they construct the FED data sets, they also introduce this FED metric. So basically, the FED matrix is used the follow-up evaluation for to evaluate the current response. This means that a unique advantage of dialogue is that we can always check how well we are performed based on the reaction of the other party, means the person we are chatting with. So that's why this matrix leverages such advantage. So they collect a list of for each dimension, such as interesting, they collect a list of positive follow-up, like for example, I say something, I want to tell whether what I say is interesting, then I check whether the the other party by reacting like, wow, that's very interesting, or the other party say something like, that's not very interesting. So we want to see the probability of generating such follow-up utterances conditioning on what the previous context and what I say just now. So it's kind of intuitive. This metric is kind of intuitive. So the author relies on the pre-trained dialogue GPT model, a large language dialogue specific language model, to predict this kind of conditional likelihood. Then they use here the P here is a set of positive follow-up, N is the set of negative follow-up. So if the probability of generating positive follow-up is greater than the probability of generating negative follow-up, then it means that what I say is interesting. Then otherwise is not interesting. So that's the main idea behind this metric. Sorry. So let's check then again. Let's check the performance of FED. So because this is a fairly new data set, and there is not many prior work baselines. So the author try to compare the proposed, they use different variants of the dialogue GPT model to do the comparison. So actually, because compared to the human upper bound we see just now, some are like 0.8, some are like 0.7. The performance of the FED is kind of fair for both 10-level evaluation and dialogue evaluation, especially for the overall dialogue level evaluation, is 0.4, which is kind of good enough, but there are still like room for improvement. So next, after FED, then in 2021 A0, actually we proposed this dialogue eval framework to try to evaluate the dialogue level coherence. So it's specifically targeting the global coherence of the dialogue. So basically we treat, because dialogue can be seen as a multi-turn interactive process between the speakers. So there are two aspects that are kind of essential to this interactive process. One is the speaker level dependency, which means that the relationship between the speakers, like the ordering of speaking. And the second is the utterance level dependency, which is the semantic relationship between different utterance pairs. So these are two types of relationship. And in the paper, we try to adopt a acyclic direct graph to model such a hierarchical structure. It's kind of intuitive way to study and to model these two types of relationships. So here is the architecture of the dialogue eval metric. I will not go into every tiny details of the model. So basically, I will just roughly tell each module what each module does. So for this S-Robota is basically a robot model that try to encode the utterance into the corresponding sentence vector. This D here is the original dialogue, like human multi-turn dialogue. The D bar here is like we perturb the dialogue, like we randomly replace some utterances so as to create some sort of negative samples. Then after that, they are fed into the LSTM. So after the S-Robot, then their embedding vector are fed into the LSTM. So this is to capture the sequential flow of the utterance. For example, this utterance from speaker A, from speaker B, and from speaker A again. So it's a kind of sequential, want to capture the sequential context. Then after that, we use the LSTM output as the node embedding initialization for graph construction. Then here, we try to connect the relation, the age is kind of try to model the relationship, the speaker level relationship and the utterance level relationship. So we use another GCN to like kind of do the feature transformation from the original node embedding to a kind of a different set of embedding, which captures which aggregate the information from the connected labels. Then after that, we want to, because for each dialog we want to obtain a single representation, so we adopt some sort of pooling layer, min pooling or max pooling. We can obtain a single vector for each dialog. So after that, after a fully connected layer and a sigmoid function, we can obtain a single score for both D and D bar. Then we use the margin ranking loss to train the model. Yeah, so here is the margin ranking loss. So if the label is 1, so means that D is preferred over D bar. Label is -1, then D bar is preferred over D. And because, so here is two sampling strategies we use to obtain the negative sample. One is utterance replacement, the other is utterance level shuffling. So this one is perturb the semantic, and speaker level utterance shuffling is to like change the order of the utterance. So it's to manipulate the coherence. And the training data sets are the commonly 3 data sets we introduced already. So this convai2 is basically a larger set of personal chat. So here is some, the right is some statistics of the dialogues. And if we look at the performance, the first task we want to see is the binary classification. So we want to see whether dialogue eval is able to tell coherent dialogue from incoherent dialogue. So we can see that compared to baselines, it's actually performed quite well in discriminating the coherent dialogue against the negative ones we generate with this utterance replacement and speaker level shuffling strategies for both all the 3 data sets. Then we look at the correlation of the dialogue eval. So compared to FED, FED we introduced previously. So in terms of coherence, dialogue level coherence performs significantly better, as well as the overall quality. So based on the result here, we can see also that dialogue eval and FED is kind of complementary of each other, because because FED is specifically tailored for, they have a different set of follow-up utterance for different aspects, so they can capture a different quality fair enough. But dialogue eval is only like designed for coherence evaluation, so it's not very good at dimensions such as diversity and on something like understanding. So they are kind of complementing each other. If we combine them there, they may perform better. But we can see that their performance is still far from the human upper bound. So there are still room for improvement. So the second last matrix I'm going to introduce is DEEM, which DEEM is an improvement of the dialogue eval. Basically, they criticize that the previous methods such as dialogue eval only rely on like text level heuristic perturbation strategies. So this type of manipulation may be insufficient to reflect errors in more advanced dialogue systems, such as the recent blend board, so on and so forth. So they try to apply the abstract meaning representation for semantic perturbation, such as co-reference inconsistency, irrelevancy, contradiction, and decreased engagement. These 4 types of semantic level perturbation. Then here is basically the detail of the metric. So basically they adopt a Robota model and a classifier on top. So it's a classification, sequence classification based Robota, but they try to classify the original dialogue here and the ARM-based perturbed dialogue. So they first try to convert the original dialogue into ARM-based representation, then do some manipulation according to the some manipulation specific to each perturbation. Then after that, adopt the pre-trained ARM-to-text generation model to reconstruct the dialogue. So they try to discriminate this one, the original one, with the generated dialogue. So that's a basic architecture of DEEM. Then here is basically some example of the the arm representation of the conversation. So and here we introduce the steps, the flow of the flow of the generation. First is to use the pre-trained arm parsing model to translate the conversational text into directed and acyclic arm graph. So this arm graph is basically a logical representation of the semantics of the sentence. And then the graph also contains the relation age between the entities, or something like the relationship between you and the Sesame Street, something like that. Then after that, they will perform some specific manipulation on the arm graph. Then after that, they adopt a pre-trained arm to text generation model to convert the perturbed graph back into the conversational text. So here is the details of the each perturbation strategy, the irrelevancy, co-reference, inconsistency, decreased engagement, and contradiction. Due to time constraint, I will just introduce one. So for example, after passing "Have you watched Sesame Street" into the arm representation, we have the node, the watch, then they kind of like perturb this node to like listen. So it's like kind of change the graph structure. Then after that, they generate this perturbed arm structure back to the text form, like it becomes "you listen to Sesame Street." So it's kind of still it's a kind of adversarial sample. So after we change "Have you watched Sesame Street" to "you listen to Sesame Street." So basically that's more advanced way of perturbing the text. So in terms of performance, we can see that here the correlation compared to both dialogue eval on the FED dataset in terms of coherence and overall quality, the DIM model actually achieved significant improvement. So the final matrix I would like to introduce is a FANDI eval model, which is published in EMOP 2022. So we observed that the correlation of DIM and dialogue eval with human evaluation is still not very strong. A major reason is that the perturbation strategy only targets dialogue coherence. If you recall previously, we mentioned that dialogue level, there are many fine-grained qualities, but these two existing metrics, they only target dialogue coherence. So we should consider more some metrics to model those fine-grained dimensions. So this paper, fine-grained automatic dialogue level evaluation, targets such multi-dimensional evaluation to the dialogue level. So the categorization of dimensions based on the FED data set, we can see that they introduce 11 fine-grained dimensions, but some dimensions are quite correlated. I mean, are similar to some dimensions. Some are quite different from each other. So we don't want 11 fine-grained different dimension matrix for each dimension. So we want to like metric for one group of them. So we try to do some analysis to cluster this 10 fine-grained dimension plus the overall, okay, into different groups, like different clusters. So the clustering is basically based on the correlation of human score of the human score of different fine-grained dimensions with the pairwise with each other. For example, the coherence and the understanding, they highly correlate with each other, like 0.8. So we can put them together. So similarly for other dimensions. So in the end, we obtain 6 groups. So in this paper, we just model the first 3. Then, so basically, we for training the submetrics, we adopt a similar preference learning framework that we use to train dialogue eval. But it's just we adopt different sampling strategies for different groups, like coherence, likability, and the topical depth. And the submetrics are combined through ensemble and multitask learning. So for coherence, basically we adopt the utterance order shuffling and the QA relevance scoring technique. So the utterance order shuffling is basically random permute the order of the utterances in human dialogue. For the QA relevance, is more pertaining to the understanding aspect. So if we try to adopt a pre-trained QA evaluator to score score the QA pairs within dialogue. The higher the score, we think that the chatbot is kind of understanding the user. And if the lower the score, so it's kind of not understanding. So there's two strategies for coherence. Then for the likability, so we adopt another two strategy. One is contradiction scoring and the number of utterances that carry positive sentiment. For example, for this number of utterances carry positive sentiment. So the more utterances that are positive, we think that the dialogue is more likable. There are some, the user feel the chatbot is more interesting. The lower number, then is less interesting. So also for similar for topic depth, we adopt this interment scoring technique to evaluate to model this dimension. So for example, we try to show that different utterance pairs, if they are semantically similar, we think that they are less information conveyed. If they are like more semantically different, like the interment score is lower, then the information may be higher. So in this way, we can train a submatrix pertaining to topical depth. Then lastly, we combine them through ensemble or multitask learning. Then we compare them with all the baselines. We can observe that this finely evolved matrix, the combined matrix, perform well across all the fine-grained dimensions as well as the overall dimension. So it's significant boost above DIM and dialogue evolve. So that's all for my section. So sorry for taking too long. So do you have any questions? So,
okay.
So actually, if not, maybe you can like email me or like send private message to Luis and me if you have any questions on the reference-free matrix. So I'll pass on to Luis to wrap up the presentation.
Yes, okay. Let me try to finish quickly because we have only 5 minutes left. So basically, what are the challenges and future directions that we have? So as we have seen along the different parts of this tutorial, metrics are limited in scope. They have a limited set of dialogue qualities, dimensions, languages, culture. So those kind of things we are not really focusing right now, but those are interesting dimensions that should be included in future metrics. Also, they struggle to generalize. For instance, if you change the sentence, the wordings, then the system will generate a different score that with the original sentence. So systems or metrics should be robust against these semantic variabilities on the sentences. Also, they sometimes are not strongly correlated with human judgment, especially when we are talking about real users. For instance, in the Alexa Prize last year, we tried to use one of our metrics into the Alexa Prize scores given by the users. And then we couldn't get really good results from humans. Let me share the screen again. Okay, so there are also inconsistencies between data sets, and that's made difficult also for this dimension. So there is one claim that we also need to mention here is the need for data sets that include different, that are clearly unifying the definition and terminology of the dimensions to be evaluated. We have found data sets that contains two different or different names for the same dimensions, and this makes it difficult to use them because each one is targeting the same dimension but with a different name. Then other data sets do not cover different new dimensions like toxicity, bias, coherence, hallucinations, common sense usage. All these things are required in order to provide improvements over these data sets, metrics. Then we have also fine-grained annotation. Sometimes we have only dialogue level annotations, other times we have turn level annotations. But what about long-term interaction? Do we have annotations for those? Basically, no many data sets or no data sets almost at all for covering all these different dimensions, right? Then we have seen that in other topics, in other fields like MT, Q&A, NLG, there has been a lot of progress because there are benchmarkings, because there are data sets. So we have been also with Chen and different researchers around the world, we have been working on creating this kind of benchmarkings, these data sets. We gave you here the links so you can go and check, because if you're interested in working on this topic, then definitely there are resources for this. Then what we are looking for is some of the desired properties for metrics, a strong correlation with human judgment, interpretability, as I said before, robustness against adversarial attacks. We want also to have metrics that are generalizable across different domains and dimensions that can be used for forward and backward looking. Sometimes we have only that metrics that only look backwards, but they cannot see what is going to happen or predict what is going to happen, because I say this response from the chatbot, this may create completely or break completely the dialogue. So this kind of metrics, checking what is the effect of this term into the dialogue is also important. And finally, we also want datasets that are compatible with human evaluation. So human can be in the loop for error correction. So if you're interested on more data sets or new data sets, please check these links that we are providing here. We have been working with different researchers to work on this, to create repositories with data sets so people can go use them and check the performance of their metrics. We are also running different evaluation benchmarkings, like the ones that we have during DSTC 10. So here you can see a long list of data sets that we use, we provide to the participants. It doesn't mean that we created all these data sets, but it means that we put them in a format that is easier for everyone to go and use their own metrics on these data sets. So this makes easier for people to evaluate their own models. We are currently running DSTC 11, especially the track 4. If you are interested, you can go to these two links, GitHub or Chatibal. We are releasing new data sets also for multilinguality evaluation, also for robustness. So you can see here basically the schedule of this track. At this point, we are running the track. We are releasing training and validation data, and we are planning to release the test data for around March. So if you are interested, please go to these links or check for DSTC 11 track 4, and you will get more information. Here you can see the people that we are working on this, including people from Tencent as well, and other companies. So what are our conclusions? Automatic evaluation is something very important to improve the performance of dialogue systems, because this will reduce costs and speed up deployment. We have seen different types of metrics: actor level, dialogue level, reference-based, reference-free, train, untrained. So we have a lot of things, but it doesn't mean that it's done. There are many, many other situations that we are required, like new dimensions, robustness, languages, explainability. All these things are important to provide improvement, especially what I'm saying before, new data sets, new annotations, also schemas for sharing data, so everyone can share the data and make easier for people to understand the evaluations, the metrics, the people they selected for doing the evaluation, etc. If you need repositories, we have given here a list of few repositories where you can find data, benchmarkings, libraries for performing the references. Also, we provide an overview of few papers that you can consider to going deeper into the understanding of these metrics, so you can check any of them. And finally, if you really want to start working with current state-of-the-art approaches, then for dialogue level, I will recommend you to go and make a deeper understanding of fine eval. This was explained by Chen already. Is the state-of-the-art, the current state-of-the-art on dialogue level. And if you want to move into turn level, then I will recommend you MDD eval. It's also the the current state of the art. For both of them, you will find in the paper the corresponding GitHub repository where you can find all the things, all the data. So it will be very easy for you to start working and starting working with the latest and the best versions of these current systems at this time. And okay, with this, we finish the tutorial. We hope that you enjoyed the tutorial. If you have any question or you have any request, you can send us an email and we will be happy to provide answers for your questions. If not, then we can finish here the tutorial. And we thank all the audience for being there and thank you for this opportunity of sharing with you what we are doing also in this area of metrics.
Yeah, thank you, everyone.
Thank you.
Okay, thank you.
We'll stop here.
Yeah, we can stop here. And I think the slides will be shared with the participants. So any question, just let us know. Okay. So
Okay, thank you.
thank you.
Thank you.
Bye-bye.
Bye.
Bye bye.